This is the ROS Developers Podcast, episode 86.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to all the ROS developers that are doing research on reinforcement learning applied to robotics. So that's a very difficult subject for which there is no much about it, especially if we are talking about using ROS in that environment. So there are some works using other frameworks that are not ROS and other simulators, but not many that are using ROS as their framework for programming the robots with reinforcement learning. So if you are in that field, you are using ROS plus reinforcement learning plus robots, then this episode is dedicated to you. And today we are going to talk and we are going to learn about how to speed our development of such reinforcement learning algorithms for ROS robots using GIM Ignition. But before going into that, let me talk you about the academy that we have built in the Construct. So it's an online academy that we have many courses, different subjects, everything related about robotics and ROS. So how to do everything from the theory of robotics, Kalman Filters, kinematics, blah, blah, etc., to how to apply that into ROS. For example, learning the basics of ROS Basics, TF, what is that? Programming drones, debugging, robot navigation, perception, how to create your own robot, artificial intelligence, and so on. So many courses there that you can have a look. And the special thing about our academy is that everything is practice-based. So it's not about delivering a syllabus and so on, but everything is going to be practice, by doing practice, even including everything that is theoretical. Like, for example, we have a course about mathematics for robotics. So how to apply this into robots. That's what we are teaching right now. And you are applying this into a simulated robot that you are testing and doing your programs along the whole course from minute number 1. So have a look. I will put a link on the show notes there. And you will see that it's very cool. It's a very fast way of learning ROS and robotics theory. Okay, so having said that, let me go to the person that is waiting here with us. And let me introduce you, Diego Ferrigo. Diego is a PhD fellow at the Italian Institute of Technology in Italy. Yes, in Italy, where he is doing research about using reinforcement learning algorithms for humanoid robots, especially for the locomotion of the humanoid robots. Today he's here to talk about the reinforcement learning with ROS and about the framework that he and his colleagues, they have developed for that is called the GIM Ignition. Welcome to the podcast, Diego.
Hello, everyone, and thanks, Ricardo, for inviting me today.
Great, my pleasure. We have been after this interview for several months already, right? After you published your paper about GIM Ignition?
Yes. The reference paper has been published in January at a conference, and after these 10 months, it evolved quite a lot. So I hope that in this interview we can give an overview of what's the status of the framework today.
Great. Yes, we have a set of questions in order to decipher all that and how we can use it in our robots. And then the first question that I have is, what was actually the problem that you tried to solve when you decided to build this framework?
Yep. So the goal of Gmignition is to easily create robotic environments for reinforcement learning research. So it does not provide environments ready to be used as other projects do, but it simplifies their development and it streamlines their development. So as a researcher in this domain, I find that the starting point of any project is the development of an environment containing the decision-making logic to solve. And you can do it once, twice, 3 times, and so on. And you quickly realize that you have a lot of code that is duplicated among these environments. That's could be centralized somehow. So the main idea of Gmignition is to provide a centralized way with some boilerplate code that could be reused among all the environments and allow developers to just focus on the decision-making logic without dealing with instantiating the simulator and all the common operation that typically are done in these cases. Okay. And then as a second goal is that the outcome of a reinforcement learning experiment is a controller that in this domain is called policy. And the policy...
You mean in the domain of reinforcement learning?
Of reinforcement learning, yes. And the policy can be trained in different way, and it needs some data. This data could be sampled from a simulator, so can be synthetically generated from a simulation, or can also come from a real robot if you want to target directly that without passing in the simulation step. So if you want to develop a decision-making logic that is agnostic from this, so it can run, it can learn either from a simulated robot or a real robot, you quickly understand that an abstraction layer is required. So Gmignition provides also this abstraction layer so that developers that want to develop these environments can only focus on developing the task, so the decision-making logic, and this decision-making logic can run on both simulated and real-time robots transparently without changing it, because it doesn't matter how from where the data comes.
Okay, makes sense. Well, I would like you to, if you can define something that you have used, a term which is the task. So you have mentioned the controller of the robot. We are in reinforcement learning. This is called the policy. So actually, the policy has to encode the controller of the robot. Yeah, but then you have mentioned now the task several times. So can you clarify just for the audience that doesn't have this vocabulary from reinforcement learning? So what do you call a task?
The task is the logic that takes the action that is generated by the policy, and process it. So let's do an example. Okay. The policy can provide some robot references, could be position references. So the task takes these references, send these references to a controller, does something. So and then it builds the state of the environment or the observation. It's called observation. And provides also a reward term. So all these kind of steps can be, as I was saying before, are independent from the robot. It could be a simulated robot or a real-time robot. So the main goal is being able to develop a task that contains this decision-making logic that is agnostic from where it runs.
Okay, great. Then this is necessary just because we are going to use this term in the conversation, I'm pretty sure, and then for people who is listening for the first time about that, then just to make them more sense. Great. And then, so you have this problem about simplifying, and then you have this problem about about training with reinforcement learning robots, but without so by separating from where the data is coming, either from the simulator or either from the real robot, and also from this robot or from that other robot, so you don't have to rebuild everything, right? That's the problem. And then you come out with something that is called gym ignition. So can you define what is gym ignition and how it fits into that picture? What it provides?
Yes. Okay, today, gym ignition is mainly composed by two components.
Okay.
And these two components, over time, they evolved, and they are targeting two different kinds of users. So it's not specific for reinforcement learning researchers, but also for robotic researchers that want to develop controllers.
Okay.
So I was mentioning about the two components. There is the core component of gym ignition. It is written in C++, and it's called scenario.
Okay.
Scenario stands for scene interfaces for robot input-output.
Okay.
And
very well taken.
Yes, okay. It is a nice acronym. And it is, as I was saying, it is a C++ abstraction layer of a scene. Okay. A scene, what is a scene? It is a set of a world that has models, and the model has links and joins. So it provides some unified APIs to interact with the scene. If this world could be a simulated world, could be a real world, but let's assume you are given by someone a world object, and you can extract models from this world object, and you can interact with these models by reading data from them and sending references. It doesn't matter if this world is simulated, so it runs in a simulator, and the physics is running by a physics engine, or it is the real world. This abstraction layer indeed abstracts this behavior.
The environment. So it's an abstraction of the environment in where you are going to put the robot.
Yes.
Okay.
Yes, exactly.
Okay.
And with this abstraction, you can build some code. And this code is agnostic from the backend.
Yeah.
So gym ignition does that. So if a scenario can be used for also developing controllers for normal applications, so if you want to develop a planner or a whole body controller, whatever, you can use that. And it is very similar to other solutions like PyBullet, Mujoko Py, staying in the Python world. What gym ignition does is taking scenario and providing other abstractions for reinforcement learning research. So to summarize, scenario is the interfacing with the robot that could be simulated or real, and gym ignition instead helps developing environment for reinforcement learning research.
Okay. So a scenario is something that is apart from gym ignition then?
We ship everything together right now.
Okay.
Yes, but you can think as scenario as the backend, what powers gym ignition.
Okay.
And it is written in C++, scenario, I mean, so it is very efficient.
Okay, but that doesn't mean that the users of gym ignition, the bundle, okay, gym ignition, the whole, then they have to use C++, right? They don't have to use that, or do they?
Again, it depends on the target. Okay. If you want just to use scenario is the C++ library.
Okay.
And we provide Python bindings.
Uh-huh.
So you can use it either from Python or from C++ if you like.
Uh-huh. Great. Okay. But you are not forced, right?
You're not forced. We usually use Python because it is quicker to prototype code with Python in general. But you're not limited to that. If you want to do everything from C++, you can do everything for C++. However, for as I was mentioning before, for our reinforcement learning research, there is a lot of code in Python. So it is very convenient to use Python for developing environments.
Correct.
So for that reason, we developed bindings from C++ to Python and built Gmignition, that is a pure Python package, because it is easier interfacing with many other tools developed by the community if you use Python, if you develop your environments in Python.
Okay. Then, so I have understood the role of scenario, and then that there is this second part, which is Gmignition, but I don't understand the role of Gmignition, the part that interacts with the scenario. So
sure. So it is all about abstractions.
Okay.
As I was explaining before, scenario provides abstraction of word, model, links, and joins. Okay.
Okay.
And this is either simulation or a real robot.
Mm-hmm.
And it doesn't has anything with reinforcement learning.
Okay.
Okay. Gmignition instead allows to use scenario, the Python bindings of scenario,
okay,
to develop environments that expose an interface that is called OpenAI Gym.
Okay.
Okay. So that the environment that you create using the Python bindings of scenario is compatible with OpenAI Gym, and therefore is compatible with all the libraries that interface with OpenAI Gym, that there are a lot developed by the community.
Yeah.
And plus, it also provides some helpers like inverse kinematics functions or algorithms for dynamics that are very common when you develop some environments for reinforcement learning. So it tries to provide a set of utilities and to centralize them, as well as the boilerplate code to instantiate a simulator and so on.
Okay. Now I think I got the whole picture. And so that scenario part actually can be used by any person on any different project. It doesn't have to be specifically of reinforcement learning. So they can use that because it's a very nice way of as you mentioned, is to abstract from the robot and simulation and the place in which it is built. It's a way to abstract about that. So any algorithm that want to use this, then it can use scenario by itself. And then you have the Gmignition on the other side, which is the one that is connecting to a scenario to take the of course the sense part and to act also. And then but then it's also an abstraction to the reinforcement learning algorithms that the community provides, like for example the OpenAI Gym.
Yes.
Okay, great. Okay, great. And then in all this picture, where is ignition? Because what is ignition for the audience? So that doesn't know. What is ignition?
So ignition is a suite of tools developed by Open Robotics. One of these tools, part of this suite, is Ignition Gazebo. It is the new generation of the Gazebo simulator that the community used in the past decade. The Ignition Gazebo has many advantages over Gazebo Classic. Let's name Gazebo Classic as the previous generation of Gazebo and Ignition Gazebo as the new generation of the simulator.
Great.
The main advantage of the new simulator, Ignition Gazebo, is that it can be used as a library. So you can instantiate a server object and you can interact with that from your code. So you can step it programmatically.
Wow.
If you're, as I was mentioning before, if you're used to other alternatives like PyBullet or JocoPy, you know what I mean, that you are the one that steps the physics when you want. And before, with Gazebo Classic, this was not possible because Gazebo was running as a separate process. And if you wanted to interface with that, you had to pass through either ROS or anyway, you had to develop some plugins to interface your code with that. Instead, being able to allocate a Gazebo object in your code and being able to programmatically step the simulator provides you a lot of freedom, a lot of control, because you are sure that if you want to step for 2 milliseconds, you step for 2 milliseconds, and you don't have to rely on any network transport for interfacing with the simulator. And this is very important when reproducibility.
Okay. What do you mean by reproducibility? What do you mean?
Reproducibility, I define reproducibility as the possibility of running many times the same code and getting exactly the same results every time. Yeah. So before, with Gazebo Classic, this was very difficult to get. And you had to rely on blocking messages, but it is not very common. Most of the people were using a middleware for or any network transport for interfacing their code with Gazebo Classic. And every time there is a socket in between, you cannot be sure that a message that is sent from your code reaches the simulator exactly in the same time, because it could depend on the load of your system, right? Yeah. So having the possibility to use Ignition Gazebo from as a library, it means that it runs in the same process of your code. And since you step the simulator, you are in full control. There is no network transport. Exactly. And this means that you can set and get the data very, very precisely. And this provides the reproducible behavior that is very important for robotic control and for reinforcement learning, where reproducing the results is already very difficult. And having at least simulation that are reproducible, it is the minimum we can do in order to improve the current situation.
Okay, great. Then, so we covered a lot of things on that initial question. What is about the part of Ignition on this framework, on the GIM Ignition? And now I think that this is clear for the audience. Then, let's say that I am a ROS developer and then I'm convinced. So, Diego, you convinced me. I want to use GIM Ignition. So I want to do one experiment of reinforcement learning for making my robot learn how to grasp this ROS Developer's Mac. Super cool. $9.99 on the online store. Just taking the opportunity to say it. So jokes aside, then so what does this developer does he has to do in order to use your framework for teaching the robot to how to grasp this object?
Well,
let's say in a sorry, Diego. Let's say this in a simulation. Okay, so we have the simulation of that.
Yes. The main point of this framework is being able to simulate robots without middlewares.
Okay.
So in this case, the idea is not using ROS, at least in the beginning.
Okay.
So is performing large-scale simulations, developing environments that can run in multiple processes in parallel on clusters, for instance, by minimizing the effort. I don't want to create any data transfer that I don't need. So the single environment runs in a single process, and there is no network transport involved. Then ROS, how can come in the picture? A middleware.
Mm-hmm.
A later stage, let's assume I have a policy that works well in simulation. And I train my policy with this setup. And I have also a physical robot, and I want to execute this policy on the physical robot.
Correct.
Here, the interface with robots usually comes in the form of a middleware. So I have to deal with the middleware somehow.
Correct.
So the ROS can be used as a backend of scenario.
Okay.
So I said before, just to refresh, that scenario is an abstraction layer, and we provide Gazebo scenario that is an implementation for interfacing with models simulated with Ignition Gazebo. However, if you want to use the same code that uses the same API, but if you want to interface with your real robots, you need a backend implemented with ROS.
Correct.
Right? So this is where ROS comes in the picture. If you have a backend for ROS, you can take your environment developed in Python and you can execute it transparently without changing the code of the decision-making logic also on your real robot. And this transparency is dealt by scenario, and in the first case, it uses the Gazebo scenario backend, and in the second cases, it will use the ROS scenario backend.
Okay. I don't know if I have correctly understood everything, because it was quite abstract what you mentioned. And then, so if I have understood at the beginning, you mentioned that in order to create the policy, the control policy, then ROS doesn't need to be there, because we are training with that simulation that doesn't need to be running anything about ROS in there. So we train it. But then when we have to apply into a real robot, then we are forced to use this policy on that robot with that specific interface. So this is interfering, actually. The ROS framework is interfering in the policy behavior, because, I mean, it's adding its own effects to the control of the robot, right? Because the ROS control is not seamless there in the robot like it was on the simulation. So there is a problem with the sound. I think we have here. We have lost sound. It's
yes.
Okay. It's
Can
okay.
you repeat the question, please?
Oh, yes, sure. So then, okay, let me see. So, okay, I think it's correct here. I don't know. Is in your site? Can you hear me?
Yes.
Yeah. Okay, great.
I can.
Okay, great. Then the question is, so I don't understand why so how would it work, the policy train on the simulation, if there is no ROS in the middle? But then you use this train policy on the real robot that has ROS in there. So how would that work? Because the ROS in the middle is not like water that is not transparent. That's what I was looking for. So it's not transparent. So it's adding its own effect in controlling the robot?
Yes, I understand the question.
Okay.
This is all about the sim to real gap. So it depends on how you simulate the robot and what you expect from your policy. The policy could behave well or drastically fail on the real robot. And this definitely can happen and can be dealt with. Yes, can be approached in different ways. Either your policy is robust enough that the effects introduced by the middleware are more or less compensated somehow.
Exactly. Yeah, exactly.
Right?
Yeah.
Or you try to improve the training, introducing the middleware also while training.
Yeah, exactly.
So I think this is what you wanted to ask me.
Yes,
so,
correct.
The possibility to run with the same code, the environments on different backends helps a lot in this case, because let's assume, as you were saying, I have a policy training simulation. I want to keep learning also on the real robot. I don't want to do only the inference just to run. And this might fail depending on how you trained the policy, right?
Yes, that's right.
I want to refine my policy on the real robot.
Well, now on the real robot. So the one that you have trained on the simulation, it's more or less trained, but when you put on the real one, then it doesn't. But then you could keep the training there. You keep the training on the real robot. Yeah. Okay.
So how would you do that?
Yeah.
If you don't have the abstraction, you have to rewrite everything.
Yes.
Right.
Correct.
From scratch.
Exactly.
You have again to get data and send references. Yes. You have to implement everything again. And we developers, we are lazy and we don't want to do that. So the aim of Gym Ignition is reusing the code and being able to run it also on a different backend. And here it is another point where ROS comes in the picture, because I change the backend, and this means that the decision-making logic can still work, because it just uses the scenario APIs. It is an abstraction layer, and depending on the active backend, it can sample measurements from the real robot instead of the simulator. And so the training could keep going also on the real robot.
Okay, great. Now it's clear, that one. Okay.
Yes, I understand that it is a framework that is very flexible. You can do a lot. And selecting just one use case, also for me as a developer, it is not straightforward, because you can really use many combination of that.
Yes, exactly. But that's given, this power is given by the abstractions. Every time that you put an abstraction, then this is allowing you to put whatever it is on the other side, and then it's going to work. But then at the same time, it's a little bit more difficult to understand, and especially to explain by words without showing any slides with the blogs and an example and so on. So but I think we are doing great. So we are doing our best here to explain to the audience and so on. Then I have you more or less have the answer the question, which is about the OpenAI. So how does? But can you clarify a little bit more? How does OpenAI get into the picture?
Yes, sure. I think this is a key point. In the community of reinforcement learning, OpenAI Gym, it is a pure Python interface, an abstraction. It allowed to separate clearly what is an environment by what is a policy. Okay, what is the agent? Okay. So this is the interface, and this means that if you want to develop environments, you just develop what you want to develop and expose the OpenAI GIM interface. If you want to develop algorithms, you develop your algorithms that get data and set actions on this OpenAI GIM interface. So it clearly separates the two worlds. And the community provided a lot of tools or frameworks from both sides. I believe that there is also something more about this separation, because the possibility of developing independently the environments from the agents triggers a virtuous cycle. And what I mean here is that often the availability of new environments trigger the development of new algorithms to solve them, to solve their decision-making logic, right? And when the algorithms get better, the environment developers can develop more challenging environments, and so you close the loop. And what I believe is that in the past, the community saw this cycle in few domains, but still, in robotics, there is no established tool to do that. And one of the trigger that we had for developing GIM Ignition is providing all the tooling for triggering this virtuous cycle also for the robotics domain.
Okay. And does that mean that we can, for example, use all the reinforcement learning algorithms that have been built inside the OpenAI GIM and then use it directly inside the GIM Ignition?
Exactly, yes. The itself, GIM Ignition doesn't contain any algorithm. It is just the environment part. Yes. Then you can use the algorithms from OpenAI, you can use the stable baseline, you can use RLib, whatever you prefer.
Exactly, because the nice thing about that is that those implementations of the basic reinforcement learning algorithms included inside the OpenAI GIM, they are very, very good implementations. So we know they work. We don't have to debug. We just want to use it. And then we can grab them, download from the Git, and then plug it directly into the GIM Ignition. And once we have our environment done, our scenario running with an environment, a robot, and a task that we want to solve, and then we can tune that algorithm for our own purposes on that there. But we don't have to have this basic implementation done by ourselves and make mistakes and make errors, introduce errors or whatever.
That's correct.
Okay, great. And what about another thing is, you also more or less answer that one, which is about the decision for taking Ignition as the simulator instead of Gazebo.
Yeah, the decision of choosing Ignition Gazebo over Gazebo Classic, I mentioned that before, is about the possibility of using it as a library, something that was not possible with Gazebo Classic.
That's one.
And I know that there were attempts to use Gazebo Classic for developing environments, but I found them always a bit difficult because they require some network segmentation if you want parallel instances and so on. So if you really want, you can do it. At the end of the story, it's still software. If you take the right action, you can do everything. Maybe it's not the most efficient implementation, but you can still find a solution for your problem. But in our cases, I didn't think that was the way to go. Okay. It was more or less 2 years ago when we started the development of GIM Ignition, and it was Ignition Gazebo was still there, was not as mature as it is today, but we felt like it was the right time for start using it to build something. It was a bit of a bet because it was still an early stage,
Yeah.
but in these past 2 years, it has improved a lot,
Yeah.
and the effort that Open Robotics is putting into it is really a lot. It is improving really fast, and we are happy about our choice. It was the right moment to start interfacing with that. And the most important feature that attracted us a lot about Ignition Gazebo is their plugin-based structure. And I'm gonna explain a bit better, since it is a very crucial point for us. The Ignition Gazebo is basically a rewriting of Gazebo Classic, and the developers managed to split very efficiently all the components that previously were all together inside Gazebo Classic. One of these components is the physics. So before, you could use only the physics engines that were supported by Gazebo Classic, and they were all bundled together. You could not have any freedom to add your own. Ignition Gazebo instead deals with physics in a plugin way. So physics is one of the systems that run in your simulation, and this system loads a plugin. This plugin could interface with the Dart simulator, as right now the default physics engine is Dart, but it can also interface with any other plugin, and the community now can develop their own Ignition physics plugin with their own super fancy physics engine, and benefit from the entire ecosystem of Ignition Gazebo, that is the rendering, the GUI, and all the other parts of the SDF and so on. It just switches the physics engine. For us, this is very important, because when we discovered that we could switch physics engines so easily in just one line of code, we can just load Dart and simulate with Dart, and in the future, when other physics engine will be implemented, load Bullet or load any other physics engine. So from our point of view, doing reinforcement learning research, we see that as taking domain randomization to the next level. So maybe it's better to explain what is domain randomization in this domain. That is, in order to obtain a more robust policy from the training process, what can be done.
Wait a second, but robust, you mean that what has been trained on the simulator can be transferred directly to the real robot and is going to work more or less. Okay, that's what we mean by robust. That's what we mean.
Yes.
The more robust, the more equal is the policy being executed in the real robot than what we train.
Yes. Many people perform an operation that is called domain randomization. That it means that you take a simulation, you try to randomize some quantities, like you can randomize gravity, you can randomize the mass of your robot, you can randomize the friction between the feet and the ground, and so on and so forth. However, usually this is done in a single physics engine, and we know that one of the most different parts between physics engine and physics engine in how they deal with contacts. And this is a very delicate point. So in order to improve the robustness of the policy, what we would like is to not only randomize gravity, mass, and so on, but randomize the entire physics engine. So changing also the contact implementation So in this way, possibly the policy could be more robust because it's so at least 2 or more implementation of how contacts are simulated, and possibly it will also work better when deployed or executed on a real robot.
That's a cool idea. Have you tried in at least in a small example? Have you tried something?
The stage of development of today is that we have a full implementation of Dart from the Gazebo point of view. So we only have one physics engine.
Okay.
So this is what I meant before with the bet, because I know that I saw some recent progression on the Bullet backend. So I'm quite confident that we're gonna see soon a second backend for as a physics engine. But this possibility for the community to develop and integrate their own might allow in the future to have more and more. So yes, it is a new framework, Ignition. It will become in my opinion, the new standard, because Gazebo Classic, the current version is the last one. It will only see some maintenance. Exactly. So this is what I meant with the bet. We are developing everything, and in such a way that as soon as they are going to be implemented, the switch will be straightforward. But today we have only one physics engine, that is Dart.
Okay. So let me tell you that I don't know if you are aware, but on the Gazebo Classic, you can also change the physics engine. And actually I think that there are 3 implementations, the ODE, the Bullet, and the Dart. I think that, I'm not pretty sure. If
OpenSim, I think.
OpenSim, okay.
OpenSim, yes. I am aware, but again, as I was saying before, the scaling simulations of Gazebo Classic is not straightforward.
Yes,
and
that's right.
We want to do that.
Okay.
Yes, it does not have reach feature parity with Gazebo Classic on this point of view, but we hope that this gap will be filled soon.
Okay. So please let me know when you publish those results, and you are able to do the experiments with different simulator engines, physics engines, and then I would like to know what are the results. It's very interesting. It's a very interesting idea.
Thanks.
Okay.
And to conclude, to reply to your question, another important feature that we like about Ignition Gazebo is Ignition Fuel. That is a database of objects that you can drag and drop literally in your simulation. So often you need to structure your world with many objects, with many models, and often you struggle to find these models. So you, as a researcher, you don't want to waste your time to create a rock or something like that, right?
Yes.
So Ignition Fuel is an effort to collect all a lot of models and making them available to the community so that everyone can reuse them and contribute to enlarge the collection.
That's great. Yeah, I have seen it. Also, drag and drop and put in this, and then it appears on the simulation. It's very cool. It's very cool. Yeah. Ignition Gazebo is getting very good, and it's improving very, very fast. So yes, I like it also. And then what else? Let me check my questions. So can you tell us a little bit more about the architecture of GIM Ignition in terms of the environment, task, and the robot? So you have divided between those 3 parts in your article, and then what are the relations between them? what each one is in charge of.
Okay. Today, the abstractions of Gym Ignition are slightly changed from the publication. We realized that they have limitation, and we improved them. Right now, we have the task, what we were discussing in the beginning.
Yes, exactly.
We have the runtime, and we have the randomizer. Okay. So to refresh, the task contains the decision-making logic of the environment. So how to process the action, how to create the observation, and how to compute the reward, and compute if the environment is done. But this is a class. The task is a class that you put, it is generic. It doesn't have to know anything about Gazebo, or it just operates on APIs given by scenario, by this abstraction layer on scenario. So the task is independent, can run on real robot, simulated robot. Then there is this concept of runtime. The runtime provides the glue code, or again, the boilerplate code that creates, for instance, the simulator. If you want to run your task in a simulator, or it handles real-time execution if you want to execute your task in a real-time setting. So basically, you take your task that is agnostic from the runtime, and you execute it wherever you have to. So the runtime centralizes the how to execute the task.
Yes.
And it is the class that exposes the OpenAI Gym interface. The Gym environment interface. So
we will plug our Gym interface. We will plug it there into the runtime part.
And so when you have your task ready and you use our runtime, since it is boilerplate code, we just provide it for you. You have an environment ready to be simulated, for instance, if it is a simulation environment. However, often it is also required to randomize the environment, so add objects or initialize in a different way. And this piece of code is specific to the simulator or to the real robot, because maybe in the simulator you have to reposition the robot in different places, or in the real robot instead you have to wait to do some manual operation, because maybe you have to reset, so you have to take the robot, maybe it fell, and you have to position it in so the randomizer is an environment wrapper that, for those that are familiar with OpenAI Gym, knows what a wrapper is. So it takes the runtime and it wraps by a randomizer and provides all the code to initialize in a different way the environment.
So you have changed then the whole structure originally. And do you have any additional paper that explains all those? Have you published any update of that? No.
Not yet. We recently released the first stable release, V1, literally this week. And
this week? So this week, another time that the ROS Developers podcast is providing some news that nobody else knows, So this week, because today is Wednesday, so it could have been Tuesday or Monday, so no more. So it's very cool, very cool. So,
and the
you were mentioning that it was published this week, the version number 1.
Yes, and we revamped, we improved the website so that now all the new information of what changed with respect to the publication, it is explained in the website.
Okay, great. I will put a link to all that, to the new website, to the old article, because it also contains very interesting insights, even if it's outdated already, but it contains very interesting information.
Yes.
And also to your Git and so on. So it will be on the show notes, and everybody that is listening there, you can go to the notes and grab more information, grab the code to start practicing with that. Okay, and then let me ask you, let me see a couple of questions more, okay?
Sure.
Well, three questions more. So to which specific and concrete problem have you applied the framework? So tell me, for example, something like, okay, so I have put this robot to learn how to open the door when somebody comes, and then it detects that there is a person, then it opens, and then we can put the door in any position and so on, so it can open. I don't know, any example, any concrete example that you have applied.
So in the past few months, we are running the very first experiment with the framework, and I'm researching about humanoid robot locomotion. And currently we are simulating the iCab robot, that is the robot we own, for push recovery. So this means that we are trying to teach how to stand and how to react to external pushes. So the process is, as I was mentioning before, so developing an environment where the robot is standing and a randomizer is applying external forces and external pushes to the robot, and the policy, the controller that is learned should indeed learn to how to react and not fall.
Okay.
And in this case, the task encodes the decision-making logic of reacting to these forces and not falling.
Exactly. Okay. Very, very clear and concrete example. So since you are in the process of applying this and getting results, so please let us know when you have the results, and maybe publish a video. So if you let us know, then we'll transfer also to the ROS developers out there. We'll like to know.
I will.
Yes, we'd like to know. Okay, another one. So then this is mandatory, this question. Does it work with ROS too?
Well, as I was saying before, it is the same reply of ROS 1. So
exactly,
you can develop a scenario backend, ROS 2 scenario backend, and your environment will run on your ROS 2 controlled robots, as much as it can work in a YARP-based robot if you implement the YARP scenario backend or any other middleware you like.
Yeah, exactly, because you have made that abstraction, so it actually doesn't matter what is on the other side, right? It doesn't matter.
Exactly.
And now that you mentioned what is this YARP thing, can you explain to the audience? Because I have used it in the past, because I also worked a little bit with the iCap in some projects in the past, and then it was running the YARP. And can you give us just a little bit description about what it is?
Yeah, very quick. ROS is a middleware, so it is something that allows different processes to communicate between each other, and there are many solutions to solve these problems. YARP is another middleware that is developed by us, by the Italian Institute of Technology, and it is the middleware we selected for controlling and interfacing with iCap in this case. It is not standalone, because we interface also with ROS. It is not. What I mean is, it can be used to communicate also with other middlewares, and for instance, we can write and read also from ROS topics. But the main aim is to control iCap with at the interface to get measurement and set references in another way that is not ROS.
Yeah, actually, I think if I remember correctly, URDF was developed before ROS, and the idea is exactly the same. It's the same because it has the topics, it was the subscribers, the publishers, the messages, and it's the same. So it's like two things that have been developed at the same time. You know, like Tesla and Edison with the current, the alternate one and the continuous one. And so it's the same. So it's very, very is very, very similar. So just for the audience there, that it does exist an alternative to ROS. So URDF is one of those. So in case, I will put also a link to URDF in the show notes in case that you want to have a look and see if that is maybe, I don't know, you want to try other ROS, but don't do it too much because this is the ROS Developers podcast, okay? But, okay, just joking, you know. Then final question for Diego. So what are the plans of the future for the framework? You mentioned before about that you are working on those different physics engines, adaptations and so on, but anything else that you can tell us and we can be waiting eager for those future results?
Yeah, I think it is important to outline what are the limitations because the limitation will define what are the next activities, next what's coming next for this project. So today there is no sensor support. So Ignition Gazebo, as much as Gazebo Classic, support cameras, lidars, and so on, many types of sensors. Today, we don't yet expose them to scenario. Okay. So I already have a partial implementation of cameras. It is almost there, but I didn't want to add it. I didn't manage to add it to the first stable release, but that's definitely coming. Then, as I was mentioning before, the only backend of scenario that is completed is the for Ignition Gazebo. There is not yet a ROS backend and not yet a URDF backend. Again, I have a partial implementation of a URDF backend, but it still requires some work before being released. And I think that will be released in the next months. Okay. And this is not much a limitation of Gym Ignition, but most of the simulator is that, as I was saying before, it only supports Dart today, but I'm quite confident that more physics engine will be developed, will be integrated in the future. And something I would be really excited to see, even though not many mentioned that in the past, is the integration with physics. For who knows what is physics, is a physics engine from NVIDIA.
Okay, PhysX.
PhysX, exactly.
Okay.
And what's nice is that it allows to run the physics engine on GPUs to execute
and multi GPUs and distributed between computers and so on. Yeah, it's very powerful.
Yeah. Now I am not sure if performances will be good until you try, but in this domain, I would really like to see Gazebo that runs a simulation with physics, and the simulation runs in GPU, and this allows to simulate hundreds, if not thousands of models altogether. Yeah. And I think this could be, especially for reinforcement learning, could be really a turning point.
A push, yeah. That's very cool. Yes. Very cool point. And I think that PhysX was not included into Gazebo as one of the supported engines, Gazebo Classic, because at that time, it was not. But the reason is, I think it's because at that time, it was not open source. But now it is. Now they have released that as open source a couple of years ago or 1 year ago or something. NVIDIA released it, so it was a movement for making that. And it's amazing. That's a very cool idea. Very cool.
Yes. So I really look forward for that. And something else is that as much as physics engine, Ignition Gazebo also abstracts rendering engines. And right now there are 2 rendering engines that are supported by Open Robotics that are Ogre and Ogre 2. And in my opinion, there is a high demand of realistic rendering in this domain, but not only. And the abstraction that they provide can provide a powerful way to get photorealistic rendering with different rendering engines. So all those that need this feature right now, if Ogre 2 is good enough, or in the future, if other powerful rendering engines will be implemented, I think this is a good reason for keep having a look to this framework.
Okay, great. Sorry. Anything else for the future?
Last comment.
Sure.
I think that it was discussed before in another episode of your podcast with specific on the new Gazebo simulator.
Oh yes, with
over
Luis
there.
Pubel. Luis Pubel,
Exactly.
the main developer. Yeah.
So probably I would redirect all the listeners to this podcast, to this episode, to know all the details just on the simulator side.
Okay.
Over there, you mentioned about the capability of distributing the computation using Gazebo Ignition that is supported. We do not yet exploit this support.
Okay.
When I was mentioning before about parallel instances of environments, every instance has a different simulator.
Okay, I see.
Okay, so we do not yet exploit these big worlds with many models, and each model is simulated by a single process.
Yes.
We duplicate the entire simulator.
Yeah, well, that's also an advancement, and it's very, very useful because you can train in parallel different policies, or you can have a set of policies that are jumping from one world to the other. So once it's trained here, then on the other, then on the other, or different policies in parallel at the same time. So that's very cool. But this is the island parallelism. But then there is another one, which is I don't know how it's called, but it's like the real parallelism. The island parallelism is when you have an island where everything is contained, but then you can duplicate this into several things, but they cannot interact between each other. When they interact, they become a same island. So in the real parallelism is like you have the super big, and so every part of that is simulated by one process, which can be in one machine or in another, or infinite machines. So that's very difficult yet. I think that the one that is closer to that is the PhysX. PhysX is doing this kind of real parallelism, but not 100% sure. Okay, so thank you very much, Diego. So it's been an hour talking here about the Ignition, and we have learned a lot. So the only thing that remains is that the listeners, come on, start practicing. Okay, you have to start practicing. Go there, do your test, and also provide some feedback to Diego and his team about how you are doing, and if you are developing anything else that can be added also there. Do you accept, right? Some pull requests and so on?
Absolutely, yes.
Okay. They need help. in order to move faster. And then all of us, we are going to benefit from that. Okay, so thank you very much, Diego, for being here at the podcast.
Awesome. Thanks for having me.
Okay, and that is that for today. But before going and finishing the podcast, let me tell you that we would like to know about your opinion of the podcast. So please send us some messages and tell us what you think, what you would like to have here on the podcast, what you would like to change or to add. Any suggestion is okay. So in case that you are watching this as a video in YouTube, you can leave us a comment below. Or if you are in the podcast, then please check the email that is on the show notes. It's an email where you can send us your suggestion, okay? So that is all for today. Thank you very much for listening, and see you next week with another lesson from the expert. And until then, keep pushing your ROS learning.